Yeah, so today is one of the many. Hopefully, every week we should have one kind of this kind of session. It's keeping in mind your projects and because the standard AI that we are teaching is more streamlined and more broad. And some of you may be finding it very basic, but it's necessary that you need to go through that. So today what I'll do is some of the advanced topics. We'll start today. So today what we'll do is RAG. This is needed for people who are working with chatbots, people who are working with any kind of question answer system. Could be chatbots is the most common. So I saw a lot of projects doing chatbots. So we thought, I don't know how many of you have started exploring or started using RAG and maybe just give you a push to do it so that you understand it conceptually well. Now, RAG stands for Retrieval Augmented Generation, but it has a interesting story behind it. So we will talk about that story. It's not a story in the sense, whenever people talk of RAG, in the same breath, they talk about another technology called fine-tuning. Now you need to understand in the next 15 minutes, when do I do fine-tuning to my transformer and when do I use RAG? This is an important skill. Now, what is fine-tuning? Basically taking a pre-created LLM, which already exists, and then training it with a particular set of documents or a particular kind of data so that it stops hallucinating on that kind of data and becomes more specialized or more specific to that data. So that is typically what is called fine-tuning. Now, how is it done? Well, fine-tuning requires you to first of all have access to the transformer code or to the basic LLM engine, and then you have to run it through a bunch of cycles with your data. That is, you have to tokenize your new data that you are bringing, and the weights of that transformer are going to get updated. So it is not something external, but it is something very intrinsic to the transformer which is going to change. And obviously, when you apply fine-tuning to a transformer, the transformer becomes very specific to that kind of data. If you see you getting it used on any other kind of data, it may not deliver the right result. So people have done this with legal information. So they have the legal BERT or the legal transformer. People have done it with real estate information. People have done it with a specific domain of drug discovery. So people have used the fine-tuning technique, basically fed it a lot of documents and then ensured that the parameters change. Now, if you ask me how many parameters will change, well, you can control some of that. Just as in transfer learning, we can control in such a way that only the last part of the pipeline gets changed. We can do something similar with fine-tuning also, that we can say that only the top stack in the transformer gets changed. The remaining stack remains unaltered. That is possible to do, and you just have to freeze some part of the transformer and only allow some part of the transformer to adapt to this new information. The only problem is it is expensive because you have to use an A100 or a expensive machine or a hardware in order to do that fine-tuning. And the second problem is, so it's cost-wise high, and the second problem is it gets so tied to that particular domain on which you have trained that it becomes practically useless for some other domain. It ceases to be a general purpose LLM machine and it becomes a very specialized LLM product. If you are fine with that and you have enough application for that, by all means you should go ahead and do it. But often people don't do it. because information, if it is dynamic, you don't want to hard code it kind of in the architecture of the LLM. You would like to keep it outside. So normally, when you have to make this decision, you have to ask, what kind of information am I dealing with? Is the information going to change? Is the information going to expand? Is the information going to update? If that is the answer is yes to any of these questions, you shouldn't be using fine tuning. You should be using the other technology, which is RAG. So you should be clear. If I am going to use this platform only for a specific set of documents, you have an argument in favor of LLM. Now, are there many applications which do this? Yes. In fact, right now, I think the Teleparadigm team is working with defense on creating an LLM from scratch, from bottom up, on their documents. Again, their documents being defense documents are very specialized documents, restricted to only missile domain, and they are not going to change much. What they need, it's all the technical manuals which they want the LLM to assimilate. And once it has assimilated, it could be used across their lab for any kind of clarification or purpose. Lot of enterprises also create their own LLM using fine tuning. Because, for example, let's say you are working for a company like Cisco. Now, Cisco has a huge amount of information about their technical products, technical literature, technical manuals. All this, they want the LLM to absorb, to suck it in, and then they want to supply this LLM to their internal customers, not obviously to the outside world, but to their internal customer, or even probably to the outside world. So it is a Cisco LLM, which is very focused on Cisco products, and the changes are not going to be too often. Why? Because, you know, once in a while Cisco will release a new product, and then they may want to produce a new LLM. But by and large, the manuals are standard, manuals will remain same, and if it is so, an LLM becomes a very good alternative. And companies have done this, and a lot of people are now finding huge amount of employment in creating specific LLMs for specific domains. It's a very interesting exercise. Now, when you are designing a fine-tuning architecture, one of the challenges in India especially is, you know, how do you do it if you don't have an A100? What is the methodology you should use? Now, we'll cover that in a later session. We have let's say we have a cluster like we have of, let's say, 15, 16 GPUs. So how are you going to distribute training in such a way that part of the training is done on one GPU, part of it is done on another GPU, part of it is done on another GPU, so you don't have to have necessarily a powerful machine like A100. You'll still need it for the mainstream training, but for fine-tuning, you might get away with having a cluster of GPU machines and doing part of the training on each. Now, that is a technique which is again an important technique for all of you to know, that how do you do fine-tuning in a lab where there is no A100, no H100, but you have the smaller machines, and how do you distribute training? You know, what is the methodology? So that's one thing which we'll cover in another session, not today. So the other thing, now I've talked about fine tuning. I'll have to show you how to do fine tuning, especially on a distributed architecture. We'll do that one of these days, because that's a technique you should know. I would be very upset if you graduate and don't know how to do fine tuning. It's like, you know, not knowing the mother lode. I mean, then what do you know? Because companies have a lot of assignments for doing fine tuning. Right? The other technique which we are going to discuss today is obviously RAG. There is another close cousin of RAG called GAG. RAG, as I said, stands for Retrieval Augmented Generation. GAG stands for Graph Augmented Generation. Both are good techniques. Today we'll talk RAG. In another session we'll introduce GAG, because you need to know how GAG works, because in certain kinds of data, in fact extremely conceptual data, it has been found that RAG is not as good as GAG. So we'll look at situations where GAG is important. So let's talk about RAG. So I think you know when will you use RAG? When the information that you have is dynamic, it's ever changing. Then it is not worth absorbing this information and fine-tuning your parameters of your transformer. It's worthless, because if the information is changing so often you know, you are bringing in new information, then you might as well go with RAG-based technique. In RAG, what happens? Use an external document in conjunction with the LLM. The LLM is still there, but it's used in conjunction. The LLM does not suck in the information. The information is kept in a separate database, what we call the vector database. So we have a vector database which can come from various companies. There is Pinecone, there is FAIRS, or there is n number of people who make these vector databases. So what do you do there? Just to give you a roundup view, let's say your LLM is there, which you don't want to touch. You can't, for various reasons, want to change the LLM. You don't have the wherewithal to change the LLM, or the application does not demand changing the LLM, whatever may be the reason. So what do? You get those extra documents, maybe 100 documents or 50 documents or whatever documents. What do you do with those documents? As usual, like any good transformer, first step is what? What do you do when you see text? Sorry, there you are. First step, this should come in blood. When you see text, what do? You look at text and stare at it, or what? You obviously tokenize the text. So you have to employ a tokenizer, tokenize the text. And once you have tokenized the text, what do you do with that text? Now you need, that is called embedding. So you basically, let's call it, okay, I like that word. Let's say you create embeddings from the text, which is one step process. Take the text, create its embeddings, right? And embeddings have to be very rich, have to be very dense, and okay, you create the embeddings. Then what do you do with the embeddings? You put them in a vector database, right? You store them in a vector database. Now that is called indexing. Now the vector database doesn't store the actual content. It stores only the index which you have created. That is, the signature of the documents gets stored in the vector database so that it can be used for referencing data, just like any indexing technique. So your data is tokenized or created an embedded document. The embedded version is used to produce an index, and that index is added to the vector database. So the vector database has the index. That is a second step. After tokenization, you add it to the vector database. Now, somebody asks you a question. This is the only thing you need to do. That's it. RAG is over. Now, you ask a question. Somebody asks you a query. We call it a query. When somebody asks you a question, what do? You are assuming that the query is on this extra data, right? So you take the query, go to the vector database, and before you do anything with the query, you have to embed the query. Good. So you embed the query, go to your vector database. On one side you have the query embedding, on the other side you have the documents embedding. What do now? You ask the vector database to match. Now in order to do matching, there are various kinds of algorithms which most of these vector databases give. What are the kind of algorithms you see? One algorithm is cosine similarity. Other kind of algorithm is, some kind of inverted file organizations where, some kind of clustering is done or some kind of inner product is taken. Sometimes it's Euclidean distance. There are 1000 type of ways, where your query can be matched to a vector, to the vector database document. Once you are matched, and depending on how many documents you are interested in, because then you have to define how deep you want to go. Typically people say, I want the top 5 documents which match this query, correct? I don't need all the documents. What will I do with all the documents? I want, let's say, 5 documents which match my query, which can be used to answer my query. Very simple. So I've got those 5 documents, I've got my query, then what do? Then I take these 5 documents, take this query, 5 documents in embedded form, Query also in embedded form. It has matched, right? So I take all this information, take the documents, of course, when you bring it out from the vector database, you want to bring text documents, and your query can also be in text form. So you take all this, the matched documents and the query, put it all together and give it to an LLM saying, these are the documents, these are the query. Now these documents are a subset of your, they need not be documents also, they can be pieces of documents. This is the content I have, and this is the question which the guy asked, based on which I retrieved these documents. Now what you should do? Take these documents, take this query, and do what? Generate an answer. Very straightforward. Generate an answer and give me an answer. So I will give that answer to the user. Done. That's all it is. It's as simple as that. This is called the basic 101 of RAG. Now I will go through this process again, then we will go through code, and then you will do a small exercise. Okay, very simple. So step 1, take your documents which you propose to add to your basic LLM. Take those documents, encode them or embed them, convert them into embeddings, put them in a vector database as index. They become the index in the vector database. Done. Then take your query, embed it, take the query embedded version and the vector database, and ask the vector database what documents match this query. So some comparison happens in the high dimensional space of embedding, and you get output as a bunch of documents, maybe in the text format. So you get those documents back in the text format, and once you get also the query, which is also in the text format originally, take that, put it together, give it to an LLM saying, these are the documents, this is your query, produce an answer. Produces an answer. So it's just intelligent prompting and the technology is done. Very simple. And some people want to make a project out of this. Doesn't even take 15 minutes to do this, correct? How long does this take? 15 minutes? Maybe 20 minutes. And then if you have to create a chatbot, what do? Just create a face on it. The questions come from a chatbot and the answers come from the, what we just described, from the RAG. And give the answer. Another half an hour. Done. That's all it takes. If anybody takes more than 1 hour to develop a chatbot with given information, the joke is on you. It shouldn't take more than an hour. That's what normally it takes worldwide. 1 hour. You agree with me? No. Chatbot should be developed in 1 hour. Given 10 documents I give you, and a question answer system. Should it take more? No, I am just asking. Should it take more than an hour? Do you really believe? I don't believe. It shouldn't take not more than an hour. And if you can't do it in an hour, I don't know. Okay. So we will go through the code which goes into a RAG, and we'll go step by step as I'll try and elaborate on each step as we go. Then we'll set you a small exercise which plays with the RAG or plays with the program, and let's see how you do it. Okay. So we will walk through the program. Yeah. So this is what we will do. We'll use FIRE. What does FIRE stand for? Why is it so popular? Nothing. No reason it's popular. I don't even know whether it's popular. Because most of commercial code that I have seen uses Pinecone. Well, it is popular because it's free, one. And it comes, Facebook uses it a lot. It stands for Facebook API for something. Okay. Sorry? For similarity search, correct. So that's why it's popular, perhaps. Okay. But everybody seems to use FIRE, so let's go with it. Then import torch, import random, import numpy, sentence transformer, import sentence transformer. What is a sentence transformer? What is a sentence transformer? Well, it is one of the embedders. It helps embed a document into a bunch of vectors. It's one of the better embedders. Produces very, see what is a better embedder? Produces very dense information. Then it is a good embedder. Okay? It is a very rich embedder. So there is a sentence transformer. Then because you need some amount of cosine similarity for doing a similarity search, you need that. Then you need a tokenizer for tokenization and a GPT-2 head model. Perhaps if you're using a transformer, okay, I think from there you can get a embedding also. Okay, and you get an LLM model, some kind of LLM model. Yeah. So we will start now. As we do on Tantric, we have the data, we supply the data. So we will give you the data. So there is a bunch of documents residing in shared data, data sets. Okay, so we are opening. Yeah, you also open this notebook so that you can see it as we go.
Yes, please log in, connect to KMIP Audi and open up. There is a notebook called as practice notebook which is already open, and you will see the bunch of files or path, so you can do parallelly along with the sub.
This is the one, the RAG FIRES student practice notebook. So, okay, you can fill it as we go. I am anyway showing you. With open, so we are taking that file. So this is a file which will contain all the documents that we want to use for our RAG generation. So we read the all the files. Rather, the file consists of many lines. Each line we are treating as a document because we are dealing with very small data. We don't want to load our cluster. So each line is a document. I mean, not in real life, but in this example, each line is treated as a document. So when I do read lines, you know, you get a list of documents. Okay. Achha, one thing which I have a general comment. See, when you are going through a bunch of Python code, one of the things I normally do is I always keep looking at the shape of the data structures which I am getting generated at various points. That's one of the best ways of understanding what's going on in the program. So please cultivate that habit that whenever you see a line of code, try and understand what is the output shape which is produced. Like, of course, this is pretty obvious, but I would be always curious if you say document.file, document is equal to file.readlines, what am I getting? What is the dimensionality of documents? What kind of data structure is it? Is it a list? Is it a matrix? Is it what kind of thing it is? You should always be looking for that. What data structure are we using? So, okay. Then there is some bookkeeping on the documents in the next line, which is we are stripping the documents which are not, we are stripping the documents, or rather I should say, we are retaining the documents which are not empty. So if you see that line, it is just ensuring that when I do a strip and it is not blank, then I retain that document, the stripped version of that document. So I'm getting rid of all the white space which may be there in the line. So that's generally a useful step. So we are doing that. Then we are sorting the documents alphabetically. This is just to keep track of what documents there are. I don't know whether it's necessary to sort the documents. We can do perhaps without that. Okay, and then we have number of documents loaded. Acha, no, before that, I think before we went here, okay, number of documents loaded, in this case we are getting 30. Before we go there, just a small, this is a small quiz. No, you don't have to do it, you just have to answer with me. Where there are some 4 or 5 scenarios, and we ask you for this scenario whether you should use fine tuning or you should use RAG. Because see, that is a decision you have to take. implementing RAG or implementing fine tuning is not a big thing. How long does it take? As I just said, RAG you can do in an hour. Fine tuning, if you are going to spread it over a cluster, it takes a couple of hours to do. How long does it take? So, okay. So, we'll do a quick, before we get into the code, we'll do a quick thing. You have to identify the appropriate use case. You have to identify the appropriate thing you should do. Should you do it with RAG or should you do it with fine tuning, right? Yeah, let's see how many of you get it right. So you are building a chatbot, which is a legal assistant that needs to provide accurate, up-to-date answers based on changing laws, regulations, and case law updates. Your goal is to allow legal professions to query large sets of legal documents without frequent retraining. The situation where you will use this actually you can sell. There is something called, in India, we have our entire legal information is in a set of documents. What is a document? What is the place you would go to build an LLM for your family on all the cases which have come, let's say, over the last 20 years. You understood my question? I'll say it again. Your parents asked you to build a nice chatbot for them. If you have sat with your parents or sat with your office, you would have seen they have a lot of information which they have whenever a client comes. In India or in elsewhere in the world, one of the things you need to do is you need to quote precedent. In such and such case in the past, this was the decision. So you have to match the current client's matter and get the precedent. Precedent is very important in Indian law, not Indian law, everywhere in the world. In that case, in 1985, this decision was taken, then it becomes bearing, and if a court has given a decision like that, you can use that decision to justify your prayer or go against your prayer, whatever. So, what would you do? There is something called All India Reporter. You must have seen those big books. No, yes? Okay. So, in India there is something called All India Reporter, which has all the cases. Now it's available in, earlier it used to be books. Now it's available in electronic form. So you can assimilate all of that, take a basic LLM and train the LLM on this information, and it will become a good LLM, which lawyers can use. Lawyers will straight away pay. But you know what is the problem? All India Reporter doesn't update very regularly. Cases are coming every day and judgments are given every day. So, let's say you provide a service every month. What will you do? You'll use a RAG on the basic LLM. So, first you'll sell the LLM and then you'll say every month or every fortnight you'll give a patch. What is a patch? It's a RAG application, something like what we are going to see, which does what? It adds to your LLM. It doesn't change the LLM, but adds to your LLM so that 90% of the information comes from All India Reporter. 10% of the information will come from this new updates which may have happened in the last couple of months. So, for this question, your goal is to allow legal professionals to query large sets of legal documents without frequent retraining. What will you use? RAG or LLM or fine-tune LLM? You'll use RAG because the operative word is dynamic. There is change. See, changing laws, regulations and case law updates. There are quick updates. This is very true of legal community where new case law is emerging every now. Every day there are new judgments, new interpretations. So you'll use RAG. Okay, next. Okay, scenario 2. It's obvious, no? For this kind of case where you have insurance application, now insurance policies don't change often. LIC has been peddling the same insurance policies for the last 50 odd years and will continue to do most of it till another 50 years. So you can use a fine-tuned LLM. Okay, next. Moment you see words like latest information, relevant academic papers, recent research findings, latest course material, this for students, for exam preparation, right? Obviously last question papers, all of that, new material, new syllabus, okay. So it's a RAG application. Okay, next. Then when you say don't change often, fine tuning, simple. Now this you tell me. Why RAG? What is toxic 50 years ago is toxic even today, no? No. New toxic language is introduced. That is rare. I mean, if you really see, that's very rare. I mean, how much new toxic slang is introduced? Not so much. Okay. Now, I think I would go with a fine-tuned LLM for this. Because see, language doesn't change. I know on social media some changes are there, but those are marginal. I think an LLM is fine. Okay. So anyway, these are, I don't know, what is the answer to the last? I am also curious. Come down. Well, I think I would go with a fine tune as an answer for the last one. Okay. But let's go back to code. Now, these decisions you have to make, and it doesn't take too long. Perhaps at times the solution is a combination. Maybe if it is a interesting LLM, you should first do a fine-tuned LLM and then add RAG or GAG. And you have to nicely automate this into a tool. You know, when you have the tool, you should have an update mechanism which will update so that it starts answering the questions better. It should have it's like a patch. If you understand how patches work, it is exactly like a patch. So you sell the basic LLM and then sell the patch as a part of a contract. So that is how you would sell. Okay, we are now looking at, we have read the documents. We found out documents means lines in the document. And we have seen how many documents are loaded, so we printed that, come down. Now this is normally what you do in general, because you don't want the unpredictable to be really unpredictable. So you seed the NumPy library, you seed the torch library, and basically seed the random number generator to follow a common seed. Okay, let me ask you this question. You must have seen or read literature. What is the common seed value which is used? Not that it matters. Very good. 42. What is so special about 42? First number with? Which was generated when two supercomputers were found. Okay. Anything else?
What is life? The answer of what is life.
What is life?
Was given as 42.
Okay. Good. You have done some research. There are many reasons. Find out that these are some reasons why 42 is so common. You see that in most seeding is done by 42. It never bothered you. Whenever you see such commonality, you should go to ChatGPT and find out why 42 is so popular. Okay. Anyway, that's not relevant right now, so we'll skip that. Okay. So we'll build a model, and so there is a model save path. Okay, whatever the model save path is given. Now we are loading, this is where the model is to be found. We have, I think, given the model to all of you. So that is the place where we have located the model. Now we load the model using the sentence transformer. So we create a sentence transformer which will help us in embedding document. So sentence transformer has to be there. You can use this sentence transformer or something else, but some kind of sentence transformer, some kind of tool which will enable you to embed documents should be there. People use all kinds. So we have decided to use this. So sentence transformer. Then now what do? You take the documents that you have sitting in that list and ask the model, now that the model is loaded, to encode the documents or embed the documents. So document embeddings will be produced as a result. This is the first step. So you take the documents and produce embeddings. Now these embeddings are actually an area of research, correct? So which is the paper which defines these embeddings? Sorry. Most of the embeddings are derived from one seminal paper. What is that seminal paper? I'm sorry. Huh? Attention is all you need doesn't do embedding here. Attention is all you need came in 2017. Embedding is much older. It came from Google only. No? Okay, there is a paper which I really think you should go read. It's called Word to Vec. Word to Vec, 2013, Google. I don't remember the authors, but that is a seminal paper. That is the first document you should read to understand how embeddings work, in which a lot of classic examples are described of embedding. You know, embedding as it happened in those days. Today, embedding has gone much further. I always give this classic example of bias embedding, which is, if you take doctor, subtract man, add woman, it gives nurse. This is a very common example, so which reflects the bias in the old embedding. It is no longer there. Nobody uses the original word to vec. It has been modified, refined much further, and okay. So this is embeddings. So we encode the document into document embeddings. Then we convert that output into a nice array, a matrix array with document on the x-axis and embedding on the y-axis. Now the model decides what is the dimension of your embedding. I guess if you look at the line at the bottom, there are 30 lines, so 30 documents, and the embedding is done in a 384. 384 is a very poor embedding. You agree? No. It's not dense embedding at all. It's very low dimensionality vector. What do today's models use? What is the dimension length nowadays? Sorry? 5? 512, no. Today's dimension. 384 is too low. Today it is more like 8K to 16K. So 8192 or 16384, right? So nowadays, the dimensions are very big because our compute power has gone up. Why do you have to have a richer dimension? Because then you can represent information more categorically and clearly. Consequences, obviously, the computational power is also required is very high. In fact, the whole transformer architecture is strongly predicated on what is the length of the dimension. The longer the dimension, the richness of output is very good, but the computational cost also increases. Okay, so what you have is a poor man's embedder, which is 384. In today's world, 384 is like a toy. You know, it's too small to represent things in a very nuanced way. Okay, so we'll leave it because we are not worried about the size. Now, we have the documents, we have the embedding. Now we have to bring the embeddings into a vector database, correct? So let's do that. So, okay. So here we can have a variation. Now we are first taking the embedding dimension. Now the embedding dimension is document embeddings dot shape 1. Now you are seeing why am I using shape 1? Shape 0 is the document itself. Shape 1 is the embedding. I hope you are clear in your mind. The embeddings is what? It's a matrix, row by row, each row one document. So that is your rows. And what are your columns, or what is your each row consisting of? The converted form of that document, the embedded form of that document, right? So, okay. So now we are creating files on standard GPU sources, which basically makes the files work with GPU. There are two files, one file which works with CPU, one file which works with GPU. Now we will see if you are having scalability issues, we'll ask you to change to CPU because that's smaller and faster. So right now we are using FAS GPU. So we are allocating the standard GPU sources. Then we have to choose the indexing strategy. So the indexing strategy we have used is L2, index flat L2. L2, what does L2 mean? What do you think it means? I know you may not know what it means, but I want you to take a guess. What does L2 mean? No? L2 means Euclidean distance. Okay? So the similar L2 squaring. Okay? So it's basically taking some kind of Euclidean distance. So, so the embedding dimension is taken to create the index, and we are going to use the, so right now we have only described the size of the index, what it should use. So we are saying index flat L2, not a very good indexing strategy, but will work on the embedding dimension. So we have created the index, meaning you have seeded the index. Index doesn't contain anything right now. We just created the index. Or rather, I should say we have created the data structure of that index. We have not created the index. In computer science terms, we call it, we have created the schema of the index. The schema of the index is there. Then we say, okay, now we give it the, after having created the index, we say FAS dot index CPU to GPU, because that has to be created on GPU. RES, which is the GPU resource. I don't know what that 0 means. No, I think that is the name of the GPU, the 0 GPU. On most of your machines or even our cluster machines, there is only one GPU. But if you take it on a A100, there will be more than one GPU. So you can address the GPU. So for example, the A100 has 4 GPUs. So you can say 0, 1, 2, 3. You are with me? So you can address this, you can put the index on any GPU that you want. Okay. Typically, how do you choose a GPU? Before you do this, you would go to the A100 and ask it, how is your GPU load? So then you would pick the GPU which would have the least load and put the index on that GPU. So to get the GPU number, we would query the NVIDIA A100. It will tell you, these are my 4 GPUs, and on each GPU, this much load is already there. So choose that which is least loaded. You can do it with simple 4-5 lines of Python code. They will tell you how are your GPU situation. Now if you know the GPU situation, you choose the GPU, so that is at 0 or whatever. Of course, here only one GPU, so 0. Index flat is obviously index flat, the same index that you have created. Now we populate the index. So this is the next step. We have initialized the index, it is sitting on the GPU, the index data structure is there, the indexing strategy is there. Now we have to use the index or populate the index. So first normalize L2, document embeddings. So we take the document embeddings and use it, this is only to normalize, I'm sorry. This is only normalize. Now why am I normalizing my embeddings? What do you think I get? I already have the encoded version. Why am I normalizing it? What does normalization do? Take the value, normalizes the value across the vector, right? So, yeah, essentially takes the value between 0 and 1 by doing something like what softmax does. Right? So, it makes that vector have values which are small, between 0 and 1. Something like softmax, don't immediately conclude it's softmax. I'm just saying it cuts the values so that they are between 0 and 1. Normally, it is better to do L2 with normalized data rather than with non-normalized data. The performance is expected to be better. So normally it's a good optimizing condition that before you do index setting, normalize the embeddings and then use them in the index. So all the embeddings, the embedding vector basically is normalized. Then the index is built. The index is built on that line, index.add document embeddings. So we have the index ready. So the RAG index is ready. Correct? So we have assimilated the documents in the index. We know what is where and we know how the documents are. Okay. Now let's start with the query processing. So we go to the next stage. Now we ask a query which is supposed to be fulfilled from the documents, either two documents put together or a single document, whatever. So we are now going to ask some question. So whatever the question be. First step is, as usual, using the same transformer model, sentence transformer model, that is same embedder, we should embed the query. Simple. First embed the query. So we embedded the query. Okay. Then because all our index is normalized, it means that the query ought to be normalized also, right? Mangoes and mangoes comparison. So if your index is normalized, query also should be normalized. Or don't normalize anything. Okay, so we normalize the query embedding also. Then what do? Then we do the most important operation, which is index search. Correct? So we do an index search. Remember, we are only searching the index, nothing else. So we are searching the index for the relevant documents, and it will give us, look at the search. What are we asking? Index.search, query embedding. So index already contains the embedded version of the documents. Query embedding we are just supplying, and we are saying top K. Top K means how many best documents do you want? So what it will do is, it will measure the cosine distance or L2 distance between your query and the documents themselves whose embedding you have. Whichever are the least distant, which means closest to your query, that many top documents will be picked. Does this make sense? No? Yes? Pretty simple, no? Basically what is it doing? It is saying, on one side I have the encoded query, on one side I have the encoded documents in encoded form in the index. Go and match this. So the flat indexing, which is what we are using, is a very slow indexing. What does it do? The entire index is flat, one by one. So that poor guy, what he does is, he takes the embedded version, matches with the first index, matches with the second index, and then sorts them and gives some number, and so, which is called distance, and then sorts them by smallest distance, ascending order of distance, and gives you those documents. Understood? Now, this is a very unsophisticated index match. Because we have not used any hierarchy, we have used flat indexing. That's easy to build, but slow to use. If you use a hierarchical indexing, then what would have happened? The indexing would be organized in a hierarchy. So like a tree, hierarchy means like a tree. So just like you are familiar with a BST or a binary tree, so it will search through a BST, same way it will go. So you will get a log n answer for retrieving the document. You getting me? if you use indexing search. But obviously, the time taken to produce an hierarchical index is also computationally higher, correct? You can't have both. So you have to decide what kind of indexing you have to use. If you are adding documents very frequently, then flat index is fine. But if you are not adding too many documents, then you should use hierarchical indexing, because that's a much more robust indexing strategy. Here we have used flat, okay, to make life simple. But you should explore other indexing strategies, especially if you are going to do a lot of RAG work. Okay. There is another reason why we took RAG as one of the first topics. The maximum employment in LLMs is going to come in the RAG space, RAG, GAG. This is where most of the work is going to happen. Is today creating a LLM or creating an LLM plus RAG. Same thing. What was the website giving? Information. Only thing is, it was one-side information, meaning whether you like it or not, I will give you this information. You don't ask me, what is LLM or a chatbot? You ask me, I'll give you, and it's based on all this internally, correct? So it's as simple as that. So this is where biggest employment, every company, every enterprise is going to ask for a chatbot related to its information, because everybody has documents. Today almost all documents are in electronic form. So you have to consume those documents, create index, have a query processor which again embeds, and obviously create a nice face to it and make it sound as if it's something great, so that somebody gives you money. It's actually 1 hour job, as we just talked. Okay, so now we are just printing the indices. So top 3 relevant documents, we are getting the indices. So you see the data structure of the indices. It's 1, 3. So because it's a batch, it's meant for batch processing. So it's doing that. That's why for IDX in top indices 0, you may get confused, but often these programs work in batch. Right now there is only 1 batch, so there is only top indices 0. Okay. So it will print, in this case we are printing the top 3 matched documents. We are using the index from top indices and using that index in the document array. So along with the index, the IDX is also stored, meaning the embedded index and the IDX. IDX is from where the document came. So we are using that and correlating. Next. So this is the answer. Now we have crossed, we are now into the last stage. We did 2 stages so far. What did we do? We took the initial data, created it into an index. That was the first step. We took the second step also. What was the second step? We took the query and matched it with, embedded it and matched it with the database. We got a pool of documents. Now on one side we have query, on the other side we have the related documents which are matching this query, which you have plucked out of the database and also from the document story. So now we are good enough to create our famous context. Okay. Now here again there is an issue. The wider the context, the better the answer. But wider the context means the better should be your LLM, the core LLM that comes into question. Because what is the common context nowadays? What is the size of common context? What do you mean by context? What the LLM knows before nahi. Knows before is knows before. What you give now, the size of your question. Size of your question means, see now what are you going to give the LLM? You are going to give the LLM the documents and the query, the related documents and the query. You are going to give it, no? So this is limited by the LLM that you are using. Normally the restrictions again are 8K, 16K, 24K, they are expanding, but they are in that range. The overall context, the overall number of bytes of information, you can give it to the LLM to create an answer. You are just about to create an answer. So most LLMs, including GPT-4o, 401, have a upper limit on how big the context can be. If you have too big a context, you have a problem. Now, since we are on that word context, okay, let me see how really smart guys you are. Context is the reason why I am not using one technology. Okay, let me ask you something else. Before there was transformer, what was the equivalent technology for transformers? People didn't suddenly come to transformers. No? So the problems which are now solved in transformers, what technology was being used to solve these problems earlier? Are you getting my question? 2017, 2018 onwards, people started solving this, what question, problem we are solving, for example, using transformers. Prior to transformers, what was getting used? Nothing. Did you get my question? No, yes. I'm just saying what is a precursor, what is the ancestor technology of transformers? Yeah. Anyone? Who is the ancestor of transformers? Don't ask ChatGPT. Neural networks. Neural networks is the ancestor of everything. Huh? NLP is language processing. No. Huh? RNNs. Good. So the answer is RNN, LSTM, GRU. No, yes, you know RNNs, no? If you don't know, find out in 10-15 minutes, you will know. What is an RNN? Okay? They are recurrent neural networks which were used. Now, I am not going to, maybe one day we'll talk about RNNs. I have big stories to tell about RNNs. No, what was wrong with RNNs is that they had limited context. If the context went above 100, 124, LSTMs became very complicated. So that's the reason LSTMs were not used. LSTMs means RNN. One kind of RNN is LSTM. So because they put a restriction on the size of the context. They said, I will forget. See, you have to go in the past, no, and remember. So they said, I don't remember so well. I forget after 1K. So that won't work in today's problems. You need longer context, bigger context. Bigger the context, better is your answer. If you can feed more, you will get a better answer. But then the transformer had restrictions, or LSTM had restrictions. That was the strongest reason why people threw away LSTMs and said no RNN, we want to use only transformers. So that was a big relief that context was not a problem. Okay, so in this case, we are creating the context, which is a combination of all the top 3 documents. So documents IDX for IDX in top indices 0. Top indices 0 contains all, it's a list. Top indices 0 is a list for the first batch. We are taking only one batch. It has 3 indices because we said top K is 3. Top indices 0 is the first dimension, batch dimension, which has 3 indices. Okay. So top 3 indices, whatever are the documents associated with that, they are all brought and joined together in one single document. And then we create the prompt. See the prompt. It's a formatted Python. Context is context, which we just created from the documents. Query is query, which we just got. Original query, not the encoded query. Encoding over now. We got the documents for which this was the query. So we forget all the encoding now. Now we have the context and we have the query. Context is original documents which match this query based on the index and the original query. And now what are we doing? Okay, now we are going and engaging another the LLM again. This time we are using a different tokenizer, a different transformer. So we are taking that data, we are taking a different model. This is the model we are using. Well, this is a model which is there in your directory. So we are using this model, and after we use that model, we are using the tokenizer. Then we are also getting the model from the model path. So we are having both the tokenizer and the model. Then we are doing it in 2 steps. First, we are using the tokenizer to tokenize the prompt. The prompt consists of what? The relevant documents and the query. That is our prompt. Yes? Followed, not followed. The original retrieved documents and the query together is called prompt. English prompt. It's all in text, open plain text. So we got that. We are encoding it. Return tensors PTs. I want PyTorch tensors because I want everything to happen in the PyTorch world, PyTorch space. And then what are we saying? Generate the output with limited max length. We are putting a restriction on the max length because we found it hallucinates after that. So model gen dot generate input IDs. Input IDs is what? Input IDs is our tokenized form of our content and query. So we are taking that, we are saying model gen generate input IDs, max length is equal to 130, and there is an interesting parameter there called numbeams 150. Okay, now this is a we didn't know this parameter, we also researched it, figured out. I'll tell you what this parameter means. Are you clear so far? Yes, no? Okay. Numbeams means, think with me a little. See, normally, if you remember the transformer architecture, at the last stage of the transformer, there is at the ultimate head of the transformer, there is a softmax prediction of the most probabilistic token to be supplied or to be produced. That is the final output, the next most viable token. In any autoregressive transformation, that's what we do. I am repeating again. Most of the transformers work on this architecture, that at the output they produce a most probabilistic token from the vocabulary saying this is the most likely word which should come in response to the context and the query, correct? Most likely word. Now, this is an interesting addition to that top portion of the transformer where it says, why are you restricting it to that one word? You can produce 5 words, probabilistically decreasing. Produce the most likely word, produce the next most likely word, like that do 5 words. You're getting what I'm saying? Don't predict one output word, predict potentially 5 or whatever the number of beams. Predict 5 output words. Don't restrict yourself to predicting just one word. Okay? Predict more. Why am I asking it to predict more? Because more variety will come in the answer. It's like, this is different. Now don't please confuse this with temperature. Temperature parameter is used for what? To stop it from being too wild. Okay, here we are not encouraging it to become wild. Temperature, you should keep it low. We want more factuality. We want more certainty in the answer. But at the same time, we want more answers. So this is numbeams. 5. Early stopping is, if you're getting the answer reasonably well, unnecessarily don't continue, right? So, okay. So that is the output ID. So you get some output from the LLM which says for this set of documents or this set of lines, using this set of lines, using this query, this is the answer I am producing. Right now, output IDs is only tokens. It will produce tokens. Now those tokens, most probabilistic token, next most, like that for each. I am converting that, or we are converting that. That is also in a batch. That's why its output ID is 0. Then we are saying decode the tokenizer, use the tokenizer to decode the output. That is, bring it back to English. It has so far produced only embedded versions. Remember, transformers by default will produce embedded tokens. Now you have to decode them to see them in English. So we are doing the reverse of encode, which is decode, and answer. So what will this answer be? From the produced documents, for that query, it has generated an answer. Correct? So that is the answer. So here you are using LLM only for its English. For this kind of last stop LLM, you can use a cheap LLM because you are giving it everything. You are giving it the context, you are giving it the query and saying use this English, use this query, produce an answer. So you are not looking at the knowledge of the transformer, you are only looking at the NLP capabilities of the transformer. That's all. So it can be a faltu transformer also, maybe a low power transformer also. You are not looking at the power of the transformer. Only thing what it has to do, given these 4 sentences, given this query, give me an answer which is based on this. That's all. So you don't need a very strong transformer to do that, right? So we get that answer and we produce that answer. So that's it. We are not looking at what correctness, or you may increase the dimension, you increase the size of the context, you'll get a better answer. As we said, our job in computer science in this college is not to teach you correctness, but the correctness of not the answer, but the correctness of the logic. That is what we are interested. We are not in the goal that you should get this answer correctly or wrong. As long as you get the process correctly, we are done. As long as you get the methodology of how to do it, that's more important. Right? Is everybody clear? It's not too difficult, right? I will give you this notebook. Look at this notebook as it is, because this is a notebook you want to start with today, and then we will give you an exercise to do. To do that exercise, some of it you can directly copy from the notebook. Some part is important. So you read the notebook as it is. It has all the code which we just talked about. And then there is another notebook which has an exercise.
You can just refer and do that exercise. And please let us know if you are facing any problem.
Some part of the exercise I think you can copy from the notebook we have given you. Only an additional part you need to do on your own.
Okay, how many of you tried with the in-class exercise, which is being shared? You need to execute. Okay. So how many of you are getting issue? Okay. How many of you are not getting issue? Okay, everyone is getting. So what is the issue? Oh, okay. For that, please use document.txt, try it out. Is there after that, who's getting out of memory issue? Okay. Okay, let us check that out.
Yeah, this is important. Please do this. Everyone, the notebook that we have given you, the practice notebook, if you are running it, at the last please write exit 0. Otherwise the GPU memory is not getting released. The last line in your exercise, what we have given you, please ensure that you write exit 0. Otherwise not only your code won't work, your code will stay in the GPU and block everybody else. Unless you say exit 0, the GPU does not release memory. You got what I wanted? In the exercise which we gave you, that is what I showed you. In that there is no exit 0. Put exit 0 last. Okay, and then try and then tell us whether it's still having issues. We are resetting the GPU because the exit 0 didn't happen, so it blocked. This is something you should be aware of also. On big machines, you have to ensure that you exit. Otherwise, it doesn't give back. First, try the example that we showed you.